Welcome to this lecture series in complex numbers. In this lecture, we will look at the notion of complex conjugates and let us recall a few things that we have covered so far. So we saw that the standard form of a complex number is a plus ib, where a is a real number, b is a real number, and in the ordered pair form, this is same as a comma b. Right? I stands for this pair, and the interesting property about I is that its square is -1. Okay, we looked at the trigonometric form of a non-zero complex number. So if we have a non-zero complex number z, then there's a unique real number r and real number theta, such that that complex number can be written in this way. So r is the modulus of that complex number, and theta is an angle. I would say the angle, but you can replace theta by theta plus 2 pi and so on. So let me just say theta is an angle made by the complex number with the positive direction of the x-axis. So if this is z, this is theta. You can take this theta also, but that's artificially different from theta only. Okay, so that is the trigonometric form. This applies to non-zero complex numbers. Well, if your complex number is 0, you could just say 0 cos whatever angle you want plus I sine whatever angle you want. That is, of course, 0. Anyway, so now let's so here are some problems. Three very simple problems for practice. And now let's get started with the material of this lecture. So suppose we have a complex number z written in the standard form a plus ib, diagrammatically represented here. Then the conjugate or the complex conjugate of z is defined as, the notation is z bar. Some people write z star. This is defined as a minus ib. All right, so that's the definition. And geometrically, it's just, if you have this is your z, just reflect that about the x-axis. So let me try to do that. And that is z bar. Right, so the geometric interpretation is pretty simple. Reflection by x-axis gives you conjugates. The magnitude doesn't change clearly, either you can see it geometrically or just calculate. The magnitude is nothing but a square plus b square and then the square root. So the magnitude doesn't change, it's just that the angle kind of changes from, if this were theta, then this is minus theta. The angle made from the positive direction is minus theta. Okay, so it's a very simple concept, but it's very useful, and we need to look at a bunch of properties. So the first property is that if you apply conjugate 2 times, you get the original thing back. So you can think of it as some geometric consequence, because if taking conjugates is reflection by x-axis, you reflect something 2 times by the x-axis, of course you'll get the original thing back. So you can think of it that way, or just algebraically, if z were a plus ib, z bar is a minus ib, and then z bar is a plus ib. So that way also one can see. The real part of z is half of z plus z bar. Again, algebraically, this is immediate, so I leave the algebraic way to look at it up to you. The geometric way is somewhat more interesting. So I have a complex number z bar. What is z plus z bar? Z plus z bar is something like that. And the midpoint of this diagonal of the parallelogram, if you consider this parallelogram, then the midpoint of this diagonal would be z plus z bar by 2. So that is halfway through between that guy. And of course, if you join these two lines, it passes through the midpoint. Diagonals of a parallelogram bisect each other. So that shows that half of z plus z bar is real part of z, because the point where this line meets the x-axis is the real part of z, because this is perpendicular to the x-axis and of course captures the x-coordinate of z or z bar, whichever. So that's geometrically clear. And imaginary part of z is similarly that, and it's a very similar thing, so I'm not doing it. Instead of z bar, you have minus z bar, this one, and here everything will be happening for the y-axis. Whatever was happening for the x-axis will now happen for the y-axis. So we have that. And a consequence of these two is these two. The first one says, if z equals z bar, then z is purely real, and conversely. Now, I perhaps did not define what is purely real. So a complex number is purely real if its imaginary part, let me say a complex number z, is purely real if its imaginary part is 0. So immediate from this we have that, and immediate from this we have that. So complex conjugates capture, in some sense, of course, there's nothing to capture there, but you could say in some algebraic fashion they capture reality or the imaginarity of a complex number, whatever that means. All right. Then there's this very nice property that it behaves well under addition. So you can add two things and then take conjugate, or you can take conjugate first and then add. Again, algebraically, you can prove it in a purely mechanical fashion. Geometrically, it's saying that you have two complex numbers, z1 and z2. Either you first add both of them and then reflect, or you reflect and then add. And that should be intuitively clear as to why the two things must be the same. So that's fine, and these two are not very different, so I don't want to say anything about that one. This is very interesting. It says that the conjugate procedure also behaves well under products, and that's a little bit surprising. So let's prove that. So let's say z1 is a plus ib, and z2 is c plus id. So then z1 z2 equals ac minus bd plus I times AD plus BC. Therefore, Z1, Z2 bar is AC minus BD minus I AD plus BC. Right? Z1 bar is A minus IB. Z2 bar is C minus ID. So Z1 bar, Z2 bar is AC plus, is it a plus? AC, no, again, it's a minus. AC minus BD because just basic computation. And then I will be doing minus, yeah, so I take a minus out. Yeah, so it turns out to be AD plus BC. Just applying the formula, basic computation, and we see this. And this is not, when we will look at the geometric interpretation in more detail, we will see what it is trying to say geometrically. Right now, we will be content with this algebraic way of doing things. Okay. So this says that it also behaves well under inverses. You take a complex number z, you invert it and then take the conjugate, or you take the conjugate and then invert. It's the same thing. And this also, I would like to just give a purely algebraic proof. Just take z equals a plus ib. Then 1 upon z is a minus ib upon a square plus b square. Right, that's what we saw, and that's what the inverse is. Then what do you do? So you could just say that, yeah, so 1 upon z bar is clearly then a plus ib upon a square plus b square. Sorry, I didn't mean to write that. Then 1 upon z whole bar is that, and what is z bar? Z bar is a minus ib. So 1 upon z bar therefore is a plus ib upon a square plus b square, and that is same as what we just computed. So this and that are the same because we get the same expression. So just remember that. And this is very, very useful. The absolute value of a complex number is in some sense not an algebraic quantity. It is, I would say, an analytic quantity. And it is therefore a little bit harder to deal with. But by means of this equation, we can many times algebraize the situation because squares are easy to deal with. They are much more algebraic in their nature. So let's just quickly do this again. Just take z is equal to a plus ib. Then z bar is a minus ib. And pure computation will show you that this is equal to a square plus b square. We have done this computation before. And what is mod z? Mod z is defined as square root of a square plus b square. Therefore, mod z square equals a square plus b square. So that's the proof. None of these are, of course, difficult, all very easy stuff. But it's how we use them that matters. And this will be very, very useful. Okay. So now let's put some of the things to use. I want to show that if z and w are complex numbers, then the modulus behaves well under product, right? Uh, we could have proven this at any point of time, as soon as we defined modulus of a complex number. But I delegated this to now because we will see it via an application of this one, right? So now let's prove this. So this thing is equivalent to showing that the squares of the both sides are equal. So we want to show that the squares are equal, and that is really the important thing to note. One can prove it via the very basics, but I will be going this route. So this is what we want to show. And now, what is this? This is, as we just learned, is equal to that product of these two complex numbers, which is equal to that, and that is equal to mod z square mod w square. That's the proof over. It shows that this is equal to that, and we are done. Just a one line proof. We did not have to deal with square roots and stupid multiplications. It's a one line neat argument, and it's a very important property, of course. Okay, now let me finish with this example. This is a kind of question which one might expect in some exam, I guess, but anyway, it illustrates some of the things that we learned. So z and w be distinct complex numbers with this funny property. Absolute value of z, or rather modulus of z, is that strictly less than 1 is strictly less than modulus of w. Then we want to show this funny looking thing, right? So okay, so that funny looking thing again happens to house a modulus sign. And how do we deal with modulus signs? We take the square. So we will start with the square of the thing. And this square is what we want to show is smaller than 1. If we show that this is smaller than 1, it follows that this is also true. So that's all that our aim is. So this is equal to that, as we just learned, which is equal to 1 minus zw bar upon z minus w. That will be 1 minus zw bar whole bar divided by z minus w whole bar. Okay, let me not skip a step. That is equal to this. So all we did was this bar kind of distributes inside because zw bar is z bar w bar. And for the same reason, z by w whole bar is z bar 1 upon w whole bar. But as we saw, 1 upon w whole bar is 1 upon w bar. So the bar distributes even under division. So we just distributed the bar. And now let me just mess around with this expression here itself. This bar further distributes because bars behave well under addition and subtraction also. So this further distributes and gives us 1 bar and that bar. And the denominator gives us z bar w bar. But 1 bar is 1 is a real number. And z bar w bar is again further distributes z bar w double bar. W double bar is just w, and that's it. So that's what we have. And let's just mindlessly expand. So we get 1 minus z bar w minus zw bar plus zz bar ww bar divided by zz bar plus ww bar minus zw bar minus wz bar. Okay, so we want to show that this is at most 1. In fact, strictly less than 1. Okay, let me just do one more line. So the above is 1 minus some horrible thing plus mod z square mod w square divided by mod z square plus mod w square. Okay. So to show that this is strictly less than 1, we need to show, so thus we need to show that right? That's exactly what we need to show, because we want to show that this is less than 1. And this part cancels out. So which is equivalent to showing that 1 plus mod z square mod w square is less than mod z square plus mod w square, right? Because this part just cancels off. This is a real number, right? Why is that a real number? Z bar w minus z or plus z w bar is twice the real part of z bar w. Why? You just think of this as a complex number tau, then this is tau plus tau bar, and tau plus tau bar is twice the real part of tau. Right? We saw this. So therefore, this guy is a real number and that guy is a real number. So it makes sense to subtract that from an inequality of real numbers. Of course, when we write something is less than something, the two things better be real. There is no trichotomy of complex numbers. So we are subtracting or adding, you could say, on both sides a real number. So it makes sense what we are doing. All right. So this is equivalent to showing that 1 minus mod z square minus mod w square plus mod z square mod w square is less than 1. But that is equivalent to, and this is just a factorization step, 1 minus mod z square 1 minus mod w square is less than 1. So if we can show that, we can show that this guy is strictly less than 1. But is that true? That is immediate from this hypothesis, right? So that part I leave you to check, that from this follows. And therefore, indeed, this is strictly less than 1, and hence this is strictly less than 1. Now, I wish I could do this geometrically without going into this mindless algebra kind of way. If you see a geometric way to do this, please put that in the comments. But for now, this is all I have. And as usual, like, comment, share, subscribe, and I will see you next time.